Now for the difficult part, okay? This was so easy, right? Showing that these are contravariant functors, that was like a piece of cake. Now the difficult part, it turns out it's not as difficult if you just follow the steps and keep in mind what you want to prove. What we want to prove is that this mapping between the Hom set C lim D and this Hom set in another category, in the functor category, right? So the mapping between cones, we know these are cones, and these morphisms, we know that it's a one-to-one mapping. We know that both of these guys are functors in C. We want to show that this mapping is actually natural, okay? So natural transformation, and in this case it's a natural isomorphism because it goes both ways, but it's enough to show one way that it's natural. So the key thing here is to show naturality conditions. So there is a naturality square that we have to show that this naturality square commutes, okay? And how do we build this naturality square? Well, we start with, we have to have two objects in category C and C prime, right? I mean, I'm just redrawing this picture, but here on the side. So we have this function f that goes from C prime to C. Sorry, morphism, because this is in categories. Here, these are functions because they go between sets, but in general we have morphisms. So we have this morphism, and this morphism can be mapped in several ways, okay? And in particular, these two objects can be mapped in several ways. So this is the mapping of the object C using this functor, the first functor. This is the mapping of the object C using the second functor. Now, we can go vertically here and we can say there is a mapping of this Hom set to C prime lim D. So now we have a different object, C prime, right? This mapping here is just contramap, right? This is just contramap acting on F, right? So we have this morphism F, contramap F for this functor, okay? Maps this thing to this thing. And we actually know what it does, right? This contramap F is actually equal to, if we pick, what did we pick here? We said this is like a U. So this will be U after F, right? So this maps into V that is equal U after F, okay? V is a member of this set. It goes from C prime to lim D. U is a member of this set. It goes from C to lim D. Okay? So indeed, F will take us from C prime to C, then U will take us from C to lim D, and we have gone from C prime to lim D. Okay? So I'm just recapping what I said before. There is also a contramap for this functor, right? Contramap. So this is a different contramap. This is for different functor, right? But you know, in Haskell we just call everything contramap. because the compiler figures out what we mean. Here, our brains figure out. So, this contra map, how does this work? Okay, so we said we take a natural transformation mu here, and this natural transformation has components mu I, mu j, and so on for every object. So let's pick one component here, mu I, and this mu I, as we said, right? Have I erased it? No. Well, but I rewrite it. So this one goes from C to di, right? And contra map maps it to IC delta C prime D, right? So the natural transformation here, a member of this is mu, and its component mu I at object I in our index category will go from C prime to di. And we said that mu I under contra map, right? Mu I is equal mu I after F. So we know how to go from here to here. We know how to go from here to here using contra maps. But now we have a natural transformation here. So let me call this natural transformation alpha between these two functors, right? And since I picked an object C, I'm talking about the component C of this natural transformation, right? Because for every object C, I have one morphism between these two guys, right? So this is a functor from C to set. This is a functor from C to set. Natural transformation will be a family of functions. For every C, there will be a function between these two sets. Okay? So here I have picked a particular C, and that means I picked a component of this natural transformation. Right? Remember this picture where we have these were the cones, right? The natural transformations, and these were the home sets. So C, then D, C prime, then D, and so on. Okay, so these are the components of these transformations. I'm picking one component. So this is alpha C, this is alpha C prime, and so on. Okay? And this arrow here is also this natural transformation, but it's taken at the point, at the object C prime. So this is the C prime component of alpha, right? So, we want this alpha to be a natural transformation, right? So for it to be a natural transformation, this diagram must commute, okay? Which means that if I go this way, so I map U into mu I using alpha C, right? And then I map it into mu I, which is equal mu I F, right? So that's one way. It takes me from U to mu I. This is another way, right? It takes me from the same U, gives me this U F, right? And maps it into mu I. Let's see where these guys go, right? So these both ways should give me this guy, whether I go this way or this way. Let's see what it means in a picture in the category C, right? Because all these guys have their parts of some cones, right? So here's C. So I have F goes from C prime to C, right? C prime to C. So I'll put C prime on top and C here. And from C prime to C, this is my F. Okay? Now, what is mu I? Mu I goes from C to DI. DI is at the bottom of my cone, right? It's one of the things in the bottom of the cone. Okay? So this is mu I. And what's mu I? Mu I is the mapping from C prime to DI. No, sorry, this was mu I, right? Mu I is from C prime to and from and mu I is from C to DI. So this is mu I. Right? It's important not to get lost. But if you just follow everything, you know, it's like this is mu I goes C prime to DI. C prime to DI, right? Mu I. This is mu I. From C to DI, C to DI. Yes. This is F, from C prime to C, right? And this says, it says that mu I is equal to mu I after F. Well, that's our commutation condition for the sides of the not for the sides of the triangle, but for the triangles between two cones, right? So these are the triangles that go like this. This was the second commutation condition that we are trying to figure out using natural transformation. And now we know. Now we know that imposing naturality on this transformation is translated into the commutation condition for these triangles. So now everything, all the commutation conditions are hidden, okay? They become the assembly language of category theory. Now we can talk at a higher level language. We can say we have a natural isomorphism between these two home sets. These guys are natural transformation that we call cones, right? And this is the home set in our original category C, right? And in fact, this is something that we'll see later in the future. These kind of isomorphisms, natural isomorphisms between home sets are very important. Natural transformations, natural isomorphism between home sets are called adjunctions. Okay? So there is a way of explaining limits through adjunctions. Okay? But we'll do this in the future. Okay, so that concludes the proof. Okay? I mean, this is something that in my blog I just said, you know, this is true, but I thought if I can actually, you know, move my hands rather than write stuff down, it's easier to understand because you see what the steps are and I can point at things, right? In a blog, it's really hard to point at things. So that's why I decided to actually do this. Okay, I'm not going to make to produce a lot of proofs because I know proofs are usually boring. It's like, okay, so we know it's true because somebody else proved it, especially for engineers who are interested more in, you know, reusable results rather than how they were obtained, right? If somebody else did the work for me, why should I redo this? And it's perfectly understandable. But this particular proof I really like because it gives you the feel for, you know, how you operate with these very, very abstract things, and then you get to the bottom of it and you just see that it's really simple. You know, it's like, well, the first part of the proof was just like defining a function, right? It was a programmer's job. You know, define contramap. Here's the input, one function. Here's another input, one component of natural transformation. Give me a component of this other natural transformation. And there's only one possible solution, right? This thing, on the other hand, this is not like implementing a function. This is something that in Haskell we would do using equational reasoning, right? We would say, okay, because of this, of these properties, you know, going from the definition of contramap, going from the definition of this natural transformation, this is what we get, okay? So I want to give you just a few examples of limits, okay? Maybe today I'll just do the simple ones. Well, of course, we started from one example, so it should be obvious that a product is a limit, right? So, but let's just like redo it from this point of view. So we start our index category. It's a category that has just two objects, I and j, right? No morphisms other than identity morphisms, right? Here's our category C. So any functor that maps these two will map I into some A and J into some B, right? Now we have, so this is our functor D. Then there is this functor delta C, which maps both objects into C. So this is a C. The natural transformation between these two functors is a family of morphisms indexed by objects in here. So there is one for I and one for J. That's all. So it's a tiny category. So there is one for I, and we'll call it P. And there is one for J. Let's call it Q. Right? So this is our cone. It doesn't have anything at the bottom because there was no morphism between I and J, right? So this is nothing. So the commutation condition here is void. There is no. So this is a natural transformation no matter what. We don't have to do any naturality conditions for it. Okay. And now this, of course, we take a whole category of these cones, right? So these cones are now very simple things, these natural transformations, and we find a terminal object, and that will be our product, right? So the product will be this guy, A cross B, right, with two projections that are called first and second, right? And for any other guy, there is a unique morphism between C and A cross B. Okay? So that was our definition. Now we can see that this is actually a limit of a very simple functor from a category that has only two objects. We call this category 2. Okay, and now one more example, and this is really a very trivial example. It's kind of embarrassing to even bring it up, okay? It's the terminal object. The terminal object is a limit, okay? A limit of what? What do you think? You want guys? We start with an empty category, okay? There is a category that's empty, no objects, okay? Here's a category, no objects. When we map it into our category C using a functor, what do we get? Nothing. Nothing, we get nothing, right? So the diagram here is nothing. However, in some magical way, you know, we can define cones saying, okay, well, a cone is just an apex, nothing else, right? So what's a terminal cone? Well, it's an apex that has a unique morphism from any other apex, right? Because all cones are just apices, nothing else. So it's just a limit, right? It's like these empty cones that only have an apex, nothing else. It's a weird thing. But it is a legitimate limit. There is a little clarification that I want to make, just in case I misled you or got the wrong impression. We talked about this equivalence, right, between these natural transformations and these morphisms here, right? So there's one-to-one correspondence. And I actually showed you one way, this way, right? I showed you that you can always do this, right? So if you have a morphism from C to lim D, some morphism M from C to lim D, which is a member of this Hom set, right? And you have this cone here. So let's say this is one of the projections. Let's call it mu I, and this is di, the image of the functor t acting on object I in the index category. Then you can always create a cone here, right? It's a good cone. So given M and given a cone here, you can always create a cone from C, right? Because you just connect the dots, right? You can always compose mu I after M, and that's this red arrow, right? And you have a projection that let's call it nu I, right? And you can do it for every point here, every object, di, dj, and so on. You get all these projections automatically. And all these triangles commute, right? Because this is how they were constructed. Because commuting means that this after this equals this. That's what commuting means, right? So, from here to here, and notice I did not even assume that this is a limiting cone. This could be any cone here, this guy. Right? For any cone, if I have a morphism going to the apex of this cone, I can create a new cone. So this is sort of a trivial statement. From here to here I can get easily. I can get from any morphism I can get a natural transformation like this. So that's not a problem. The problem is the other way around, right? So the question is, what can go wrong? Why can't I do this? Right? So suppose that I do have a cone here and I do have this other cone, right? What can go wrong that I won't get a morphism here? Well, first of all, there might not be a morphism here, right? We might just, this Hom set could be empty. You know, you have this cone, you have this cone, but this home set is empty, right? Or it might be too many of these morphisms, right? So it might be that there is M1 and there is M2, and they both factorize this cone, right? It's possible, right? What does it mean? Well, so let me draw this diagram. So we have M1 and we have M2, right? And this is our mu I, right? And I'm saying there could be two different M's that make this thing commute. Meaning mu I after M1 is the same as mu I after M2. Now, if you remember from a long time ago, there was this thing called monomorphism, right? Remember, monomorphisms were defined like this. Monomorphism is something that if you have two guys like these, right, that give you the same composition, then they must be equal. So mu I is a monomorphism if for every pair like this, they must be equal. So there would be a unique on them, right? But in general, these projections here don't have to be monomorphisms, right? In fact, even in the simplest cases, they are not monomorphisms. What is not a monomorphism? Not a monomorphism is something that squishes things together, right? Makes 2 points become one, right? So the squishing is not monomorphism. And just take the simplest limit, the product, right? The product, we have first and second. Is second a monomorphism or first? No way, right? Because it squishes together things like, let's say it's a product of two integers, right? It will squish together 1, 2, and so second, okay, and 2, 2, and 3, 2. They are all mapped into 2, right? So these projections are not monomorphisms. However, because they form this universal cone, what happens is that whatever this one squishes together, the other one will distinguish, right? And in this case, yeah, the other one, the first, will say, oh, this and this and this, they are all different, right? So this is sort of like a generalization of monomorphism, this limit, right? It says, well, one of them is not a monomorphism, but maybe 2 of them or 3 of them will distinguish between all these other possibilities, right? So that's the universal construction always picks up this thing that just like splits things into nice classes.